Okay, hello everybody. We are going to discuss about the chemical kinetics chapter in this complex reactions. In this complex reactions. What about complex reactions? Here, some reactions don't takes place an elementary step. Elementary step means in a single step. Such reactions proceed in a series of steps instead of a single steps and nothing but multi-steps process. This type of reactions we are called as complex reactions or stepwise reactions. For example, 2NO plus 2H2 gives rise to N2 plus 2 moles of H2O2. Okay. From the above equation, from this equation, stoichiometry equation, the order of the reaction is directly we say to 4. Why? Because here 2 moles of NO, 2 moles of hydrogen molecule. Simply, what about order of this reaction? 4. But practically this is the complex reaction. This is not a elementary reaction. Okay na? Just we show directly this is the elementary single step reaction, but experimentally this is a complex reaction. Okay, how? First of all, 2 moles of NO react with only 1 mole of hydrogen molecule. After then N2 gas plus H2O2. Actually, this is the slow step. Slow step means rate determining step also. What about second step? Here H2O2 is there. React with another mole of H2 gives rise to 2H2O. This is the fast reaction. This is a rate determining reaction. Now what about order? Order depends upon always rate determining step or slow reaction. That means 2 moles of NO, only 1 mole of hydrogen molecule. That's why the order is 3. Order is 3 is the right, order 4 is the wrong. Okay, here the rate is depends upon 2 moles of NO and 1 mole of hydrogen. The total order of the reaction 2 plus 1 is equal to 3. Okay, this is a just example of the complex reactions. In our syllabus, the complex reactions are classified into 4 types, which is consecutive reaction, parallel reaction, and opposing reaction. Last one is the chain reaction. In these 4 must be one question asking in our semester examinations. The main important one is the chain reaction is the very important. Okay, now we are going to discuss one by one. First of all, now we are going to discuss about the parallel reaction. First one, parallel reaction. First of all, we are going to discuss about the parallel reaction. Parallel reaction. What about parallel reaction? Parallel in the name is there. When a reactant undergoes 2 or more independent reactions at the same time is called as parallel reaction. For example, I am taking reacting, A is the reactant, is undergoes to 2 or more independent reactions. This is a one independent reaction, this is another one independent reaction. We get form of B and C at the same time. This type of reactions we are called as parallel reactions. Okay, and that means each independent reaction will give to one product. Okay, what about any examples is there for this reaction? Very simple, the nitration equation is there. That is the, for example, I am taking phenol. Okay, nitration, HNO3. Okay, we get two products at the same times, which is OH, the major product in the form of ortho position, that is the NO2, and next one is the meta position, OH. In this two reaction, the first one is the main reaction and second one is the side reaction. Here the main reaction, the formation of product is 90%. Here the formation of product only 10% only. 10% only. Okay. That's why this is the example for parallel reaction. Now we want to rate of reaction for the first one and second one. That's why the simple example, A gives rise to B and C. Okay. Along the way of B is the rate is K1. Here rate is K2. Rate is K2. The first one is the main reaction. This is a 90%. This is the 10% formation. In this reaction, A gives to two products, which is B and C. The first reaction is the main reaction. The second reaction is the side reaction. Side reaction. Here, A is the initial concentration of the A. A is the initial concentration of A. After some time, the A is the loss of X concentration. Loss of X concentration. What's happened? The same X concentration form as B and C concentration. And nothing but B and C concentration is equal to X. And here decomposition of A. How much amount? X amount loss. The same X amount appear at B and C. What about B? Y amount of Y concentration and Y concentration of the B and Z concentration of the C. And here and nothing but X equal to Y and Z. Why? Because here initial concentration is A. Loss of X concentration. The same X concentration will form as B and C. What about B? Y concentration. What about C? Z concentration. And nothing but X is equal to Y plus Z. Simply rate of disappearance A is equal to, we can write as minus dx by dt. Why? Because loss here ds disappearance is there. That's why indicate minus loss of X concentration with time. After then here for example at time 0, initial time, A concentration is the A, B concentration 0 and C concentration 0. Why? Because without reaction, before start the reaction, A is equal to A, B concentration 0 and C concentration 0. After some time, at time t, what happened? A is the loss of X concentration, and that means A loss of X concentration. Here B form as Y and C form as Z, and nothing but B X is equal to Y plus Z. Rate of formation B and C, and B is equal to dy by dt, and rate of formation C. What's happened? C is equal to dz by dt. A is equal to minus dx by dt, and nothing but B and C is equal to, simply we can write as dx by dt. Clear? B and C is dx by dt. Why? Because A equal to B and C, minus dx by dt. B and C is equal to dx by dt. Separate B is equal to dy by dt. Separate C is equal to dz by dt. And rate of formation of C is equal to dz by dt. Rate of formation of B, dy by dt. Rate of formation of A, minus dx by dt. Rate of disappearance of A, minus dx by dt. Rate of formation of B and C equal to dx by dt. Okay. Here, before equations, rate of formation of B and C is equal to dx by dt. Separate B and C is equal to dy by dt plus dz by dt. Why? Because previously x is equal to y plus z. After then, dx by dt is equal to, here previously already we have discussed this type of reaction is there. A, here B, here C. This is a K1, this is a K2. Here A minus X, here this is the Y, this is the Z. Here formation of B depends upon the reactant, that is the A minus X. Here also rate of C depends upon reactants constant. What about A minus X? And that means dy by dt equal to, we can write as rate is equal to K1. Here K1 depends upon A minus X. Plus after then K2. Here also depends upon A minus X. A minus X. In this, which is common? A minus X is the common. A minus X is the common. A minus X into K1 plus K2. K1 plus K2. After then, dx by x term write as here left side, A minus X is equal to K1 plus K2 into dt upon integration. Upon integration, what's happened? Integration dx by A minus X is equal to K1 plus K2 integration dt. Here integration differentiate will be cancelled. This equation we can write as minus ln A minus X is equal to K1 plus K2 T plus C. Upon integration, these equation write as in this manner. This type of reaction we show number of in our chemical kinetics, first order, second order, okay, zero order like this. Okay, upon integration differentiate will be cancelled. After then we add some constant, okay, that is the C. Okay, we wanted to see, we can apply boundary condition, that is the T is equal to 0 as well as x is equal to 0. These two terms substitute in this equation. For example, t is equal to 0. This term will be 0. Only c is there. X is equal to 0. Only minus ln a is there. I am writing here minus ln a is equal to here only c. We have c value. C value substitute in this equation. What's happened? Minus ln a minus x is equal to k1 plus k2 T minus, here ln is there, okay, plus into minus ln a. Okay, ln a term write as this type. What's happened? Here minus is there, when write as left side, plus ln a minus ln a minus x is equal to k1 plus k2 into t. Okay, ln a minus ln b, ln a by b, ln a by a minus x is equal to k1 plus k2 into t. Okay, after then here k1 plus k2 is equal to, just assume k, we want only one reactant, only one rate constant. After then we can calculate k1 and k2 individually. Okay, simply we can write as ln a by a minus x is equal to k into t. K into t. This is the final equation. But here k is equal to k1 and k2 is there.